cable bus. Design. Introduction. The design of a cable bus connection for a project will require the following minimum input parameters: ambient temperature, rated voltage and basic insulation level, rated current, rated short-time current, duration and peak. The assigned rated voltage of the cable shall be the same as the rated voltage of the cable bus. Parameters of a cable bus. The cable bus is designed for an ambient temperature of 40 degrees Celsius with a maximum conductor temperature rise of 50 degrees Celsius. Some projects may limit the total temperature of the conductor to be less than 90 degrees Celsius. All cable manufacturers furnish cross-section detailing the constructional features, physical properties, and dimensions of conductor, insulation, screen, shield, and sheath. They also provide resistance, inductance, and capacitance per unit length of the cable depending upon the constructional features and configuration. Derating factors for ampacities are also furnished for ambient temperature, if different from 40 degrees Celsius, configuration, and nature of the installation. For assigning a current rating under service conditions, a cable bus manufacturer has an option to select number of cables per phase defining the parallel paths. Configuration of cables in cable bus. The number of cables per phase increases with the increase in the ampacity of the cable bus. The single-phase cables are arranged in a matrix of a maximum of 3 rows and 9 columns while maintaining a minimum center distance of twice the cable diameter. Depending upon the assigned rated current of the cable bus, one of the displayed configurations is identified. For any given rating, it is possible to design a cable bus with a wide range of size of cables, number of parallel paths, configuration of matrix namely number of rows and columns, phase disposition in each element of the matrix. Most manufacturers have standardized on a few variants in cable sizes and optimized the configuration for a range of current ratings. Low-voltage cable bus can be of a 3-wire or a 4-wire system with an option for the cross-section of neutral being either the same or half the size of the phase conductors. If specified, an insulated earth conductor may also run at an appropriate location in the slot. A project engineer needs to be aware of a few inherent characteristics of the cable bus. When there are several cables in parallel per phase, it is difficult to imagine that all the cables of the same phase will share equal current. This will depend upon the configuration of rows and columns and the physical location of a cable, with respect to the other cables either of the same phase or of different phases. In a larger matrix of cables, the temperature of the cables in the center will be higher than that of those in the periphery. A variation in temperature will lead to a variation in the RDC, skin effect ratio and consequently RAC of the particular path. The resistance of the path will be further affected by the proximity of other conductors either of the same phase or of different phases. Each conductor will also have different inductance for the same reason. Consequently, the current in individual parallel paths will neither be in phase nor will they have the same magnitude. The current will distribute itself to keep the terminal voltage of each parallel path the same. In a cable bus with 2 improperly balanced parallel conductors per phase, the current sharing could be in the ratio of 30 to 70% of the total current. The scalar addition of the currents through individual paths will be higher than the vector addition. Therefore, the actual copper loss would be higher than what would have been if the currents were equally distributed in all the parallel paths. Such situations will also lead to an unbalance in voltage. These unbalances and the voltage drop is a matter of concern in low-voltage cable bus than in medium-voltage cable bus, as the unbalance and the voltage drop is always measured as a percentage of rated voltage. Since MV cables are shielded and LV cables are unshielded, the proximity effect will be less pronounced in medium-voltage cable bus than in low-voltage cable bus. Similarly, the assumption that the burden of short-circuit current is shared equally by all the cables in that phase is not true. This is not true even when the fault occurs outside of the zone of the cable bus connections. Should a fault occur inside the zone of connection, the faulty cable will have to carry the total burden of the fault current. It is, however, important to note that since, in most of the cases, the cables are single-core, unarmored, in a low-voltage system and they are held in position at a predetermined distance from the nearby cable, at least 1 cable diameter, the possibility of a line-to-ground fault within the cable bus is remote. In an MV cable bus, the cables, though single-core, have a shield that is earthed. On an earth fault, within the cable bus, the shield will carry fault current. Failure to withstand the fault current for its duration will lead to failure due to overheating. Fortunately, most medium voltage systems are non-effectively grounded and the earth fault current gets limited in its magnitude. Ampacity of cable bus. Given the arrangement of cables in the matrix with phase identification and spacing between the cables, all reputed cable bus manufacturers have computerized programs to evaluate ampacity based on the ambient temperature and ventilation provided by the bus enclosure. Short time current withstand capability. Equivalent resistance per phase considering the temperature distribution. Equivalent inductance per phase considering the spacing and phase distribution. Short circuit forces withstand capability to arrive at the span. Voltage drop at rated current and envisaged power factor. Power loss at rated current. Voltage unbalance. The above parameters will depend upon the phase-specific matrix of conductors and therefore can be optimized for the most favorable configuration. The capacitance of the low-voltage cable bus may be neglected. Medium voltage cables have shields and hence their capacitance to the ground will be independent of the configurations. As has been stated earlier, the prediction of current distribution, magnitude and phase angle, in each parallel path of the same phase, in the maze of a matrix with similar parallel paths of other phases, is very complex. Consequently, evaluating the equivalent resistance, inductance, and capacitance per phase is challenging. For the same reason, it is difficult to analyze the effect of short circuit forces and the distribution of temperature. The importance of conducting the short circuit test and temperature rise test for a given configuration cannot be overemphasized. Further data from the field after commissioning is invaluable to estimate the voltage drop, voltage unbalance, and current and temperature distribution. After finalizing the size and configuration of cables, project-specific layout and terminations with the interfacing equipment are carried out as per the standard practice of the cable bus manufacturer. Type of cable in cable bus. The selection of the type of cable is left to the manufacturer. The basic insulation level of the cable shall be compatible with the system. The insulation of the cable can be polyvinyl chloride, ethylene propylene rubber, or cross-linked polyethylene. The material of the conductor can be either copper or aluminium. Some of the above parameters may also be specified by the customer. Shielded cables are recommended for medium voltage cable bus as it enables uniform stress distribution of the insulation and contains the field, limiting possible radio interference. It can provide a ground path for leakage currents. Shielded cables may also be installed in low voltage connections when they are likely to be subjected to soot or other heavy deposits that may form a conducting path to ground. Size and configuration of cable in cable bus. The size of the individual cable and the configuration is decided by the cable bus manufacturer. Having decided the cable type and insulation, the size and configuration will depend upon specified rated current, temperature rise of conductor over ambient, short time rating, voltage drop, maximum conductor loss. As explained, the current and temperature distribution across the cross-section will depend upon the geometry, interphase and intraphase spacing of the conductor. Most manufacturers have a computer program that calculates resistance, considering skin and proximity effect, reactance, self and mutual, current distribution, and electrodynamic forces. The earthed enclosure around the cable matrix will impact the values of these parameters. Calculating and assigning temperature rise of individual conductors in a matrix is far more challenging since it depends upon the capability of the enclosure to evacuate the heat generated. Carson's line method of calculation is used for the evaluation of the electrical parameters. All cable manufacturers use Neyer-McGrath formula for evaluating the temperature rise for different ambient temperatures. For shielded cables, the ampacity is also dependent upon the method of grounding of the shield. The slotting of the cables in the phase is carried out in a manner that provides minimum unbalance and least voltage drop. This optimization can be carried out in a computer program. Phase transposition of the conductors is not carried out in cable bus. Having conducted type tests and field measurements on different types of cable bus, most of the reputed cable bus manufacturers will be able to justify the design, interpret the computer output, and forecast the results. Cable bus manufacturers work closely with the cable manufacturers for the data on cable and envisaged temperature rise under various service conditions. In a three-phase short circuit, the forces experienced by the conductor depends upon the magnitude and direction of the currents and distance between the conductors. The distribution of current within the parallel paths will vary due to the combined effect of skin and proximity. The vector addition of individual forces will depend upon the configuration. For medium voltage cable bus, care should be taken to ensure that shielding wires are grounded correctly. If the shield is connected only at one end to the earth, there will be induced eddy currents in the shield due to the current flowing in the adjacent conductors. These eddy currents will generate losses depending upon various geometrical and electrical parameters. However, if the shield is connected to earth at both ends, then the circulating currents will flow in the opposite direction. If the shield cross-section is not adequate to carry the same current continuously, failure could occur due to overheating. It is recommended to earth the shield only at one end while performing the short circuit test on a medium voltage cable bus. In the temperature rise test, not only will the conductors not carry equal current due to the combined effect of skin and proximity, but the heat evacuation from the conductors will be different. The conductor that is surrounded by the other conductors will have the maximum temperature rise. Since the mathematical model for the distribution of current, forces, and temperature in a cable matrix is very complex, a comparison with the test and field data of a near equivalent product will be most useful. As a very approximate estimate, an 8 volts to 10 volts voltage drop at rated current and 0.8 power factor for every 100 meters or 330 feet length of the cable bus may be considered practical. Since the permissible voltage drop is expressed as a percentage of the system voltage, this may not have much impact on medium voltage distribution but could be significant in a low voltage distribution. Span of cable bus. The span of the cable support block is determined by short circuit forces generated per unit length by the fault current flowing through the cable. The forces will depend upon the geometry of the configuration, phase spacing, and distribution of fault current amongst the cables. It is the normal industrial practice to provide a minimum gap of 1 cable diameter between adjacent cables. It is also the practice in the industry to not exceed a span of 900 mm or 36 inches in the horizontal run and 450 mm or 18 inches in the vertical run of cable bus. Grounding of cable bus. Cable bus must be grounded as per NEMA standards. Aluminium enclosure with spice plates for joining adjacent sections can act as a ground conductor. It may be earthed at 2 terminating ends. If there is a flexible rubber bellow in the run of the cable bus, the same may be bypassed by a flexible copper braid of an adequate cross-section. If the client were to insist upon a separate copper conductor run along with the cable bus, the same may adequately be supported from the side rails. Cable bus with steel enclosures must have an earth conductor running along for the entire length. Some specifications call for an insulated ground conductor to be run inside the cable bus. Arrangements can be made to comply with the same by accommodating the cable in a spare slot. The shield of the medium voltage cable shall be earthed. It is preferable to earth the shield only at one end to prevent circulating currents. When the root lengths are large, the induced voltage at the unearthed end of the shield can be significantly high. Under those circumstances, the manufacturer's advice may be sought on cable shield earthing to contain the induced voltage. When a ground fault is being fed from the cables in a cable bus, the earth fault current will flow mainly through the enclosure or earth bus fixed to the cable bus, even when other parallel paths are available. This is because the enclosure or earth bus offers the least impedance for the return path. Cable bus enclosure shall be grounded, as per NEC section 250. Losses in cable bus. Apart from the losses in the conductor, there will be induced losses in the enclosure due to eddy currents generated by the stray flux. Enclosure made from galvanized steel will additionally have hysteresis losses. Shields of cables, in medium voltage cable bus, are grounded. They will generate losses due to eddy currents or circulating currents, depending upon the method of grounding of the shield. It is quite difficult to evaluate these parasitic losses in the conductor shield and enclosure. Thank you. For a comprehensive understanding of the theory and practices of busbar systems, it is advisable to read the book An Introduction to Busbar Systems, where contents are organized in a sequence for ease of reading and facilitates cross-reference. Please procure a copy of the book with a requisition to Bala at busbarsystems.net.